That is, in the last class, we viewed this supervised learning as an optimization because in any supervised learning, input will be there and then the output will be there. And we have to find a function which will map the input to the output. A function in the sense it can be any machine learning algorithms. That is, if we take a neural network algorithm actually, then it has to find a function which will map input to the output. When we are mapping the input to the output, our objective is what? We have to minimize the error. That is, the minimization of the error is nothing but the predicted output should be approximately or almost equivalent to the actual output. That is what we are going to expect actually. Therefore, the supervised learning is viewed as optimization in the sense what we are trying to do. We are trying to find a function which will optimize this particular function. That is a minimization of the error. That is what we are going to look at. Now, when we have to minimize this particular error actually or minimize some function, we are going to look at the optimization methods which are going to help because when we in neural network what we are trying to learn, we are in the function we are trying to learn the weights because our function was y is equal to w1 x1 if x1 is the input and w2 x2 and then w3 x3 if there are three inputs. We are trying to learn this w1 w2 w weights, w3 weights. Initially we'll start with some random values for the weights actually. When we are learning to map the input to the output, we are trying to find the optimal values for the W1, W2 and W3. Now, when we started with some values and we have to find an optimal values, then we need some optimization methods or the methods which will guide us like how we can update this weight values. That is, we should update this weight values in such a way that our function of minimizing the error, our objective of minimizing the error should be achieved. That is, update the weights in such a way that our objective of minimizing the error is being achieved. For that, we are going to use, that is for this particular this thing, we are going to use a optimization methods. In the last class, we discussed about this gradient descent and then the conjugate descent. And I have given a foundation for the conjugate gradient. And I told the conjugate gradient is going to converge faster. Converge faster in the sense it will try to find the minimum of the function in a fast manner when compared to the gradient. In this figure also you can see the blue line indicates to the gradient and then the orange color line indicates to the conjugate gradient. Both are starting at the same point, but conjugate gradient is taking only 2 steps to converge to this minimum point, which is a minimum point here actually. But gradient descent is also trying to converge to a minimum point, but it is taking more number of steps actually. That is the foundation what I left in the last class was conjugate gradient converges faster when compared to the gradient descent. We'll look at why it tries to converge faster and what is the direction it is going to take and then what is the algorithm for the conjugate gradient. And then in the conjugate gradient, we have to solve the equation ax equal to b where ax is the unknown. Unknown in the sense if I take a neural network, it is a weights which we don't know. We have to update this particular system. Known is A and then the B. That is, we know the input and then the output. That is, a known parameters are A and then the B, which are going to act as an input and then the output. But unknown as the weight vectors, which we don't know. That is, solving this equation ax equal to b is equivalent to minimizing the function f of x. The f of x is 1 by 2 x transpose a x minus b transpose x, where say x is n cross 1 vector, then a will be a matrix of n cross n, and similarly this is a weight vector, sorry, n cross 1 matrix, and b also is n cross 1 vector. Now, in the conjugate gradient, we will try to find the solution for the x by minimizing the function that is f of x which has been given. Why we are trying to do that one is because when we take this function f of x, that is f of x, we can minimize if the differentiation of f of x is equal to 0. Now, when we differentiate this function f of x and considering A is a symmetric matrix and it is a positive definite, in the next slide I'll clear about the positive definite. If we take the matrix A is a symmetric matrix and it is a positive definite, and now when we try to find the differentiation for f of x, we are going to get the value, that is when we differentiate this one with respect to the x, we will get ax minus b. That is ax minus b when I get, that is now when we have equate this to 0, then it becomes ax equal to, that is summarizing in the conjugate gradient. We have to find the solution for the x in the equation ax plus b. Instead of directly solving this equation to find the value for the x, we will try to minimize the function, that is f of x equal to 1 by 2 x transpose A x minus B transpose x. We'll try to minimize this function in the conjugate gradient. Now we'll look at little background with respect to the, before going further into the algorithm of the conjugate gradient algorithm. Like as I said, that is gradient descent always takes the path in the form of a zigzag manner actually. That is, once it starts this one, and if it has to go, it goes, because it tries to find the gradient always actually and goes in the opposite direction of that particular distance. But what is conjugate is, it is nothing but the perpendicular. That is, if the conjugate has started in this direction, instead of going in the same direction, it next step, it takes the direction opposite to that one. Assuming that if we take the direction opposite to that, we may converge little faster to the minimum. That's why it takes. Conjugate is nothing but, or conjugacy is nothing but perpendicular. It takes the steps like this, that is if it started in this direction, yes, it takes the perpendicular direction of that particular this thing. That is, if this is S1, this is S2. It is something like this. That is, if I have a function like this, I'll try to find the gradient of this particular this thing there, that is f of x, and this is going in S1 here. We will try to find the opposite of that one perpendicular to this one, which is going to become the S2. That opposite direction we'll try to find. Now, as I said, A is an n cross n matrix. X and B are the vectors of n cross 1, and we assume that is A is a symmetric and also positive definite. Why positive definite? Because X transpose A X will always lead to a value which is greater than 0. It will not be 0. It will be greater than 0. That's why we call the matrix A as a positive definite. And now orthogonality actually. What is orthogonality? Two vectors when I take X and then the Y, and we say that is x and y are orthogonal when x transpose y is equal to 0. Now in this diagram you can see x is a vector with the value 4 and then the 2, because this is 4 and this is 2 here. And then y is a vector with the values -1 and 2. In the graph you can see that is this is -1 and 2. Now when you take x transpose y, that is 4, 2 and then multiplied with 1 and 2, it will lead the value, sorry, this is -1, that is 4 minus 4, which is going to become 0. Two vectors, we are going to say x and then the y is orthogonal to each other if x transpose y is equal to 0. That is, in the conjugate gradient, what I said, if we are searching in the direction S1, next search direction will become S2, such that S1 and S2 are orthogonal to each other, or conjugate to each other. That is, once we have find one search direction and we are going in that search direction S1, next search direction we will be taking, which is going to be orthogonal to that particular search direction, that is S1, S2. That's how we are going to tell this is orthogonality condition satisfaction. Now, starting with the algorithm of the nonlinear conjugate algorithm for supervised training of multi-layer perceptron. That is, when we are training multi-layer perceptron, instead of using the gradient descent, because until now in the class, when we have to update the weights wn plus 1, we took w of n and then minus of that learning rate, and then we used to have the gradient, that is rate of change of the error with respect to the rate of change of the weights, because negative direction we used to. That is how we are updating. The step size was this one, where we are multiplying the learning rate with the rate of change of the error with respect to the this weight. We called this as a gradient. We used to do this one in the gradient descent. But now we will look at in the conjugate gradient, when we have to update the weights, how we are going to do that. Now, when we start this algorithm, we'll start with that is the weight vector is available, and choose the initial weight values W of 0 by a procedure similar to that described in the backpropagation algorithm. But as when you apply the gradient descent, we use the backpropagation algorithm to update the weights. Backpropagation in the sense, errors will move from the output to the input. That is, in the multi-layer perceptron, if we have started with the input here and this is the output layer and there are some hidden layers here, we backpropagate the error from output to the input when we have to update the weights. That is, we'll start with the initialization of the W0 initial weights, and then the algorithm steps in the conjugate gradient are, that is W of 0, use the backpropagation algorithm to compute the gradient vector. That is, once we know W of 0, compute this gradient. This is rate of change of error with respect to the initial weights what we have. This is going to become the G of 0, the gradient vector. And now set the search direction S of 0 and the residual R of 0 to the negative of that particular gradient minus G of 0. And then at time step n, use a line search to find the n of n that minimizes EAV of n. That is, here is the average error. Average error of that with respect to the learning rate what we have chosen at that time instant n. Sufficient the representing the cost function E may be E average expressed as a function of the learning rate eta for fixed values of the W and the S. That is what we are trying to understand in the third step S. That is, we will try to minimize the average error function expressed in terms of eta, and then for a given fixed learning rate and for a given learning rate and the fixed for the current value. That is, current value of the W is, that is W0 which we have chosen. Such direction was minus G of 0 what we have chosen initial at the time step n. Next, fourth step, test to determine whether the Euclidean norm of the residual R of n has fallen below a specified value, that is small fraction of initial value. That is, when we started with this W of 0, so there will be some error, that is residual will be there, R of 0 will be there. Now, when we update the weights, that is at the R of n, we are not yet done, but when we update, then R of n should be less than R of 0, because your residual should get reduced by step. Then we are moving in the proper direction. Next, to update the weights, that is W of n plus 1 equal to W of n plus the small step size learning rate eta of n, and then the search direction S of n. Now, for the we have updated the weights actually, and we will now use the backpropagation to compute the updated gradient vector. That is G of n plus 1 will be the rate of change of error with respect to the updated weights, that is w of n plus 1. That is what is a gradient with respect to the new updated, and then set the residual r of n plus 1 to the minus g of n minus 1. Now, we have to use this beta parameter, because next when we have to update the search direction, we will use this beta parameter. The one way of updating the beta parameter is Polk-Ribber method to calculate this one. That is a formula, fixed formula. There is some derivation steps how it has been achieved. But to get this value, we can use this formula, which tells that is maximum of this value or 0, which is given by r transpose of n plus 1 and then multiplied with r of n plus 1 minus r of n, and then divided by r transpose of n and then r of n. Now, after calculating the beta parameter, we can update the search direction as s of n plus 1 equal to r of n plus 1 plus beta of n plus 1 and s of n. And next, you set the step size, this thing as n plus 1. And then we will go back to the step 3. That is, we continue once again calculating the step size, updating the vector, calculating the residuals, updating the weight vector, and then calculating the residuals, and then updating the beta and the search direction. We'll continue this one until the stopping criteria is met, where r of n is less than or equal to epsilon of, that is r of 0. That is when we reach some prescribed minimum error will be in the loop. This is how the conjugate gradient descent is going to work. Continuing, that is, I said for the search direction calculation, we are going to calculate this beta using this formula which has been mentioned. But there is another way which we can use also to calculate this beta, that is using the Fletcher-Rives formula, which tells beta of n equal to, that is beta of n plus 1 for the next updated this thing, that is r transpose of n and r of n, and then this becomes r transpose of n minus 1 divided by r of n minus 1. That is, we can use this formula or this formula, any formula to calculate the beta of n. That's what I'm trying to mention in this slide is, that is for the beta calculation, we can use the Polk-Ribber method or the Fletcher-Rives method. Now, that is what we understood in the conjugate gradient algorithm is, we are going to calculate the search direction. The search directions what will be calculated will be orthogonal to the other direction. That is, if you are in this direction, either we will find the direction which is perpendicular either up or down depending on the gradient what we calculate. If we are currently here, then either we will go in this direction or we will go in the other direction, actually opposite of that particular this thing, which is perpendicular. That is what which is going to ensure when we use this formulas which has been mentioned here. We will not look at the proof of this one, but it ensures that search direction, the new search direction will be perpendicular or conjugate to the previous search direction. Now, as I said, that is optimization methods in the supervised learning, we can use the gradient descent or the conjugate gradient descent. Next, we will look at this quasi-Newton method, like how it is different from the conjugate gradient and why we have to go, what was the problem we had with the Newton method, because before this we have the Newton method also. What was the problem with Newton method and why we have to go with the Quasi-Newton method we will look at, and later we will look at the difference between the conjugate gradient and then the Quasi-Newton, because we looked at the difference between the gradient and then the conjugate gradient. Now, in the context of the supervised learning, we view the training as a process of minimizing the cost function. As I said, minimizing the error function. While gradient descent uses only first order information. Because earlier in the class, I've shown this formula, that is error function expressed in the form of a Taylor series, that is error of W of n plus updating this particular weight with derivative delta of W of n. When we expand this one using the Taylor series, we are going to get this function, which is a average error with respect to W of n, and then the G transpose of n, delta of n, that is this is first order and this is second order, because uh, first order will always give the slope information for us, but second order will give the curvature information about the function. Curvature information, that is our objective is, that is this the x as axis is indicating the weight, and then y axis is for the error, slope, and this that is with respect to the slope, that is when we find the rate of change, we will find a slope is the tangent of that one, that is slope we'll try to find. But I want to know whether we are reaching the curvature or not, that is the curvature, because a curvature can be upside down or downside up, and we want to know when we reach this convex actually, whether we are upside down or downside up actually. For that, we will use the second order derivative, second order information in this Taylor series function. What we are trying to understand here is the gradient descent algorithms will use, that is EAV W of n plus, that is GT of n, and then delta W of n. But conjugate gradient descent methods, they use this both the terms along with the another term, that is a second order term, that is 1 by 2, and then delta of W of T of n and H of n and delta W of n. Here, H of n is a SCN matrix SCN matrix, which is a second order derivative, partial derivative functions of the weights present in that network. That is, we were here, that is Quasi-Newton method uses the approximation of the second order information to navigate the error landscape more efficiently. It uses all the three terms to navigate to the error function, because when we started here, that is if you take this as it is our error function is a parabola, and if we have started here, what we have to do, our objective is we have to come back to this particular minimum, because this is where we are getting the minimum of the error. We should know what weight values, or if we have started here, we should know that we have to go down and then we have to reach. Different optimization algorithms differs, like how we are going to take the step when we start with the initial values, and how fastly or how many steps we are going to take to reach that minimum value. That is what it makes the difference between gradient descent, Quasi-Newton, and then the conjugate gradient method. Now further, we'll look at the Quasi-Newton. Before going to the Quasi-Newton, first we'll lay the foundation for the Newton method optimization. That is, in the Newton method uses the SCN matrix H, which is a square matrix of a second order partial derivatives of the errors with respect to the weights. That is this example I have shown here. This F function is with respect to the weights, that is error function. Error, and this x1 x2 are going to represent the weights, that is W1 and W2. The weight update rule under the Newton method is W of n plus 1 is equal to W of n minus inverse of the SN matrix and then the gradient, that is G of n is the gradient. But now, what is the problem with this Newton method was, that is calculating the exact Hessian matrix H, and its inverse inverse is computationally expensive because it comes to the around of big of n cube, where n is the number of weights. That is, if n is the number of weights which we have to optimize, if we go with the Newton method, and now when I use the inverse of the Hessian matrix, then our time complexity will go to the big O of n cube. And if we use this Newton method in the networks like deep learning, this thing which is going to have millions of parameters, algorithm will work, but the convergence will be very slow, because it is going to take a lot of time to find the optimal values of the weight set. Now we'll look at how the quasi-Newton is going to overcome this inverse calculation of the Hessian matrix. In the quasi-Newton, in the quasi-Newton, instead of calculating exact SEN at every step, quasi-Newton method builds an approximation. We are not going to calculate the exact SEN matrix, but approximation of the SEN matrix or the approximation of the inverse SEN using only the gradient information obtained from the successive backpropagation steps. That is, B of n be the approximation of the inverse SEN matrix H of n. We are not going to calculate the exact inverse SEN matrix. We are going to approximate that inverse SEN matrix, and let us call it as a B of n. We are not going into the detail like how we are going to find the approximation, but the idea is this one. Instead of calculating the exact SEN matrix, inverse of the SEN matrix, approximate that to the value, and let us call that as an B of n. Now, there are many different variations under the quasi-Newton method, but one is BFGS, that is Broyden, Fletcher, Gulfer, and Shano algorithm. It updates the estimates of the inverse SNB at each step n based on the change in the gradients. That is how there are many algorithms, the variations. That is how we are going to approximate the B of n. One is the BFGS algorithm. That is, it updates the estimates of the inverse SNB at each step n based on the change in the gradient. That is how it is going to. We are not going in detail. I am just telling the information of it. Now we'll look at the steps what we follow if we go with the BFGSR, the general strategy of the quasi-Newton. That is, the first test we have to compute the search direction. Search direction, that is using the current gradient G of n. The current approximation of the inverse SN will be B of n, which will be minus B of n and then the G of n. We did look at how we calculate, but this B of n is the approximation for the inverse SN, and search direction will be opposite of that. Now we have to perform the line search to find the step size, that is eta of n, that is at the time step n, that is this eta of n, that is a learning rate, this one. Because see, when we used the gradient descent, I said W of n plus 1 is equal to W of n and then the learning rate and then the gradient of it. This we used to initialize. That is, what is a learning rate? That is, what is a small step size I have to take? And it becomes, it becomes fixed for all the updations until we change this particular thing. See, this itself, to know what learning rate, whether I have to use 0.01 or I have to use 0.001 or 0.1 is a question mark for us. But in quasi-Newton, we are going to find this appropriate small step size at the learning rate which will try to minimize the cost function along the direction S of n. Now we'll look at what does this line search means. That is, you look at this diagram. That is, using the line search approach, we are going to find the optimal step size weight eta of n. Now say this is a function which we have to minimize. That is the error function, because the y-axis is the learning rate eta. X-axis is the learning rate eta, and y-axis is the error. Now say we started with the eta of 1, then our error will be this one, which has been pointed here. Say next value was, say my eta was eta 3, then my error will be this particular point. If I would have chosen eta of 2, my error will be this one. That is, we are going in a line search direction. We will choose eta of 1, eta of 2, eta of 3 in such a way that error of eta of 1 is greater than average error of eta of n3, because that is what we can observe, because this, it is here and this is below, little below. Therefore, it is E average eta of 1 is greater than E average error of eta of 3. And now E average eta of 3 is greater than E average eta of n2, because that is what you can observe, because this error is above and this error is below. That is, when this that is, in the line search, if we have found 3 eta values, eta 1, eta 2, eta 3, now we can conclude that there is some optimal value which is in between eta 1 and eta 3. That is, say in this case it is eta 2. Actually it should have been here, that is some eta, but there will be some value between eta 1 and eta 3 which will guarantee to minimize the error. That is, we were in the second step of the quasi-Newton. What it says is, find the step size eta of n, that is learning rate, in the line search. In the line search, what we are going to do, we'll try to find some 3 points, eta of 1, eta of 2, eta of 3, which satisfies the condition average error of eta of 1 is greater than average error of eta of 3, and average error of eta of 3 is greater than average error of eta of 2. Then there will be a choice between, that is there will be a value in between n1 and n3. That is, this is eta. This is eta. Eta of 1 and eta of 3 here. It is not this thing. This one is eta of 1 and eta of 2. There will be some learning rate. That is, I can now have my learning rates only in this period, in this span. I don't have to go beyond this one. I don't have to go lesser than eta of 1, or I don't have to use the values greater than eta of 3. Next, we can vary the values of the eta learning rate in between eta of 1 and eta of 3. That is how we are trying to find the learning rates or the step size in the quasi-Newton. That is, third step in the quasi-Newton is updating the weights. That is, W of n plus 1 equal to W of n, and the step size what we have found, and S is the search direction. And then next, update the inverse ACN. That is, we had B of n, and next you update the B of n plus 1 using the new gradient. That is, new gradient calculation will happen using the new weights, that is W of n plus 1. That is, quasi-Newton, we then went further details only at the high level. How this algorithm updates the weights is, it first calculates the search direction S of n, which is the negative of the inverse approximation, ACN approximation, that is B of n multiplied by G of n, and then calculate the step size eta of n that minimizes the cost function along the search direction S of n, and then update the weights W of n plus 1 equal to W of n plus 1 and eta of n, and then S of n. And now recompute back the b of n plus 1, that is a next updated search direction with the new weights and the new gradient. And stopping criteria, once again, it will be same as the this conjugate gradient, where my residuals are the error is going to be minimized of some specified error is minimized for some specified thresholds are the constant, and then we will stop it. Now we'll look at the difference between the conjugate gradient optimization method and quasi-Newton method. That is, in the conjugate gradient method, search direction calculated using current gradient and the conjugacy, that is perpendicular this thing conjugate. That is, correction factor was the beta, because that we used the beta in the that is a search direction calculation, because you remember that is when I showed the uh, this thing, we used this beta parameter in the search direction updation. But in quasi-Newton, the search direction is calculated by multiplying the gradient by the matrix B. That is an inverse Asian approximation. This, sorry, something wrong. This is inverse Asian approximation. And then curvature information. In the conjugate gradient, implicitly accounts for the curvature by keeping the direction H orthogonal. That is second order information. And here it explicitly stores an approximation of the curvature in the matrix form. And then in conjugate gradient, the computational burden is very low because we store only a few vectors. We are not storing any this thing actually. That is any matrices or anything we are not going to store. But here we have to do the approximation of the inverse Hessian matrix. Therefore, we need at least n cross n matrix. And then stability. Conjugate gradient highly depends on very precise line search to stay conjugate. Always when the search direction has started, if it takes perpendicular like this, next once again it has to go with the perpendicular direction. Always it should go like this, because that is how the objective of this conjugate gradient is. But here, quasi-Newton, it is more robust because the matrix update can compensate for the less precise line searches. There is both advantages and disadvantages with respect to this method, because quasi-Newton, the computational power is very high, but it is more robust. But conjugate gradient computational power, computational burden is very less, but finding the conjugacy, that is perpendicularity in searching in the search direction, is highly dependent on the line search algorithm, what we say actually, because it may oscillate sometimes, it may not work. Depending on the problems applications, we can experiment and find out which optimizations works better for what and how we can achieve our convergence with less number of steps.